Okay, now let's get started since it's 12 p.m. So today's moderator and speaker are both on Zoom, so I'll hand over the mic to our moderator today, Dhruv. Dhruv, you can start.
Okay, awesome. Thanks, Jake. Hi, everyone. Welcome to another talk for the series this semester. This is our seventh one and the penultimate one. And we're very excited to welcome Yuanqi today. Yuanqi Du is a PhD candidate in computer science at Cornell University, where he studies the intersection of AI and scientific discovery. His research centers on developing principled, efficient, probabilistic, and geometric models that accelerate scientific discovery from hypothesis search, validation to automation, with a special focus on the intersection of physics and chemistry and their applications in drugs and materials discovery. So Yuanqi's work has appeared in leading machine learning venues, including Europe's ICML, ICLR, and featured as cover articles in top-tier scientific journals, including Nature, Nature Machine Intelligence, Nature Computational Science, and Journal of the American Chemical Society. And as a passionate community builder, Yuanqi has also organized over 20 community events, including conferences, workshops, and seminars across AI for science, geometric deep learning, and probabilistic machine learning. And I think based on Yuanqi's website, he's also going to be on the academic job market for next year. So very excited for all of that. So without further ado, over to you, Yuanqi.
Yeah, thanks so much for the very kind introduction. And it's a great pleasure to speak here about some of the recent work that I've really been interested in pushing on the side of large language models. As I mentioned, it's kind of like a general goal towards automation of scientific discovery. But our approach is a little step by little, because I'm trying to, as a computer scientist by training, I want to keep things that are well defined, the problem well defined. So, and you see this throughout the talk. And I hope I can convince you by the end of the talk, the takeaway that scientific knowledge exists in large language models, and you can extract it. All right. So yeah, before we start, I think it's always, I can show something that large language models are changing the world, the coding, the web, and just a lot of things around us. Yeah. But do they understand science, right? So as I said, the whole tone of this talk would be trying to make this problem as well defined as possible, like large model understand science. But here there's a word understand, which is not so well defined. So, but people has approached it in different ways, because whenever you need to write an evaluation or benchmark, that you have to make it well defined in certain ways. And there are a few ways people have done it. And there are more ways, I think, even more recently. But the first way is like people have a lot of experts to interact with those large language models. By large language models, I mean like GPT, Claude, and Grok, and those kind of like commercial large language models, or including DeepSeek as well. But not those kind of like open source small autoregressive models, but mostly just like large language models that are being trained at commercial level. And this is a report from Microsoft Research. This might be out of date, but I don't think the conclusion has changed. Is that you just use GPT-4 to set up a few things and to see how the quality of the work being done, right? And you can see that they didn't even put concrete quantitative evaluation, but they put in like thumb up and crying faces for different things, because they don't have very clear evaluation on those things, or it's very hard to evaluate those things. And the second one would be people take some computational or experimental databases that we have for example, for molecular structures or materials and their properties and what things that we measure experimentally, to ask if a language model do it. And now you can see they do it by they rank all of them like different types of general model. They didn't even compare with in this table, they didn't even compare with the domain-specific model, but they also actually highlight the performance in the last column that compare with domain-specific models, but their category are pretty like loose, because they call it like not competitive, competitive, selected competitive, or accurate, right? And the third one would be exams computation. There are more for them these days. I think people manage to get them very, very good for the mathematical computations and coding computations, so on and so forth. But people has also tested this chemistry, physics, and math, and this was in the old days, maybe around 2 years old. And but people tested on college level exams that not released to the public. So as a holdout evaluation on those things. So the takeaway here I want to show you is like, we really don't have a very concrete idea. So if how much language will understand science, and the way that we approach this is very qualitative, right? So we kind of like make human to interact with them or make human to ask them questions and to see if larger model be able to answer those questions. But sometimes language model make incredibly wrong answer to an easy question, and sometimes they manage to do solve some hard problem surprisingly. So even today, I don't think we have a very absolute answer about how much language model understand science in a very quantitative way. But you can see some evidence in some cases people tuned it very well. They solved problem very, very nicely. All right, so now I want to make a computational friendly definition about scientific discovery. It's a very brief one, right? So scientific discovery, usually we can start with some scientific inquiry, some goals, some problems we want to seek answers for, to ask for about nature. So sometimes we want to discover some theory that we've seen, make some observations that in physics that we want to have what the equation of motions or the physics governing laws for those questions. Or sometimes we make some observation, some metabolites that relate to aging behaviors. We want to see what the structures are because we cannot directly see this through our eyes. Or we want to design new material or new drug. We are searching over the space of the candidates to find the potentially functional materials. All right, so this is actually very computational friendly. So once you have the inquiry, that makes the problem well defined, or starting to make the problem well defined, and then you can further define the hypothesis that you are searching over. Usually it's not it's human. It's based on human heuristics or rule enumerated. It's not going to be the true hypothesis space, but we kind of like prune the space based on our interest in reality, so that we can manage the hypothesis space, and they have to be verifiable. We have to have a verifier, and usually in science we do it. The golden standard is the lab experiment, but sometimes if we have high fidelity simulation these days, or even very well-trained machine learning models are used as a cheap surrogate for those validations before passing into experiments. And this will help us derive observables. And we can refine our hypothesis and we can iterate this loop many, many times until we find a new discovery, right? But note here that scientific discovery can be of more flexible form, but I think the century, excuse me, the center of it is this iterative loop. There are a few questions to ask then. How do we define knowledge? What do we mean knowledge if knowledge exists? And how do we make sure if this knowledge is trivial, right? So if I ask a language model a simple question, and the level of trivialness has been increased over time. If you ask a question to ChatGPT, maybe when it was just released, GPT 3.5, it was maybe some question was non-trivial, but now becomes trivial. All right. So now I want to kind of like formulate this problem in a different ways, right? The goal is that we want to extract knowledge from language models. This is kind of like an evil-defined problem because we don't know, what knowledge means and what we are trying to extract, and even what extract means. But extract is we can define it very easily. Is that maybe if I ask some question, if language model be able to output it, right? So, but what I really want to do is like reframe this problem as a search problem. As you can see in the last slide, I show you the core loop of scientific discovery. You're just like iterative searching hypothesis. And once you have a predefined verifier that is fixed, then you have a very well-defined search or optimization problem that will approach day-to-day in computer science operation research. And I want to approach this through a few examples that initially actually shocked us when we first did this work. This was a work that we did around a year and a half ago. The first in science, there are a lot of problems once you fix the verifier, and they can be verified computationally. Once you fix the verifier, they become very well defined. The first example I want to demonstrate this would be I want to search some molecular structures, and they in 2D they look like this, but what language models see is really this: a list of is a strings with a list of characters to denoting the molecules. And how do I define knowledge? Is that I want to search over the space of possible molecules. I want to find those molecules that define with my verifier for certain properties. I want this property to be optimal in some sense, as good as possible. And how do I make sure the knowledge is untrivial, at least the first thing I do is like it has to beat classical search or position or sampling algorithm that people have been using for many, many years for those problems. You have to, and of course, language model wouldn't be able to answer this question in single step, which I'm going to show actually, it's actually true. Even language model has improved a lot, but for those search problem that you define a verifier and ask language model to keep searching better solutions. Language model is never, at least so far, never able to answer it in zero shot. And what kind of algorithm we want to use here? Right? The algorithm can, there are wide class of algorithms that you can, if you're interested in search, you can use some maybe Monte Carlo tree search, A-star search. But for, if you're interested in sampling, you can use some Monte Carlo method, or you can use evolutionary search. So here, we really want to emphasize that larger model are naturally probabilistic models. They parameterize their probability distribution. And the nice thing about the probabilistic model is that we want to we want to control them. We can control what distribution they sample from. And here we just took a very simple example. Back in the day, that evolutionary algorithm was not that popular yet, because it's very simple. It's very easy to implement, and they take the sampling flavor. You iterate over a list of hypotheses, and then you only keep the good ones, and you sample better ones. It's really a flavor sampling, and it's directly related to some sampling algorithm, such as sequential Monte Carlo. All right, with that problem formulation, now we are ready to talk about what we did for searching hypothesis with some oracle functions or reward functions like guidance over the space of molecular structures. And all right, so this is the figure that we have in the paper. So the idea is that you first start with some initial samples. These initial samples you can, in science, if you want to, when the scientists actually use it, they can provide some initial samples, the space that they want to explore. But in reality, like when we test this, we just start with zero shot samples. Those are the properties that we scale to between 0 and 1. And when you initially ask GPT-4 to propose some molecules that would maximize some binding to some specific target, it would only give you those samples that are actually very bad in terms of scores. And the next step you do is like you take your you maintain a pool, and you take the current samples from the pool, and you try to mate in the pool, right? So you want to make some perturbation. You want to take in the pool that you consider them as better samples from previous iterations in terms of scores. And you make some mutation to some of the structures, say, okay, can you get me something better? Or you take crossover. Difference is mainly just the crossover, you take two good ones as the parent, and you wanted to generate some offsprings from the good ones, right? And after you make enough perturbation to construct your the candidate pool for the next iteration, now you want to use your score function or this oracle function to score them, right? And you can see that maybe you propose better ones through some iterations by taking some substructures and assemble them together. And now you have a larger pool than the pool you want to maintain. And now you want to use the score function to rank the pool of all molecular structures. And then you want to only keep for example, you can have very flexible selection criteria. And the simple one would be just keep the top K. Or if you care about diversity, you can cluster those structures and using a clustering based method. And those in general helps with diversity and so on. And then after that, you do resamples. Like for getting the next iteration, you take the pool. The pools are all, you keep the good samples in the pool, and then you go through this loop again. You take the pool and you have some mechanisms of sampling from the pool and to make perturbations. And what's nice about evolutionary algorithm is like you can really look at it in different perspectives. One, you could look at it purely based on heuristic. It's a heuristic-based search, whatever you choose. Or you can really formulate it very, very well in terms of sampling problem. And then you can look at, okay, what I would do if I care about diversity, and what I would do to do this resample, how would I, make this perturbation? And after going this loop many, many times until they converge or running out of the budget of the oracle calls, you would reach your final population. And those are optimized molecular structures with respect to the properties. Now I want to show you some results. The results actually really impressed us at the first place, where there was for molecular optimization. This was even when we talk about modern deep learning, that was maybe one of the earliest field that adapts deep learning. And even if you're familiar with the graph neural network, massive processing neural network, initially people were drawing connection with them with molecular fingerprint. So this is really a field that has been really close to computation. They have been really developing many combinatorial optimization method and the generative model based method combined with reinforcement learning or Bayesian optimization Gaussian process, a lot of benchmarks over this problem. And they have developed also a long list of computational oracles. And this makes this problem very well designed test bed for what I want to achieve. And what you see is like this reinvent is RL-based method. This graph GA is like genetic algorithm, but based on the graph structure, the 2D structure instead of the strain. And this is Gaussian process Bayesian optimization. And we've shown the three type of language models. I would only the third one, GPT-4, is a large language models. But we also showcase what if you have some very small autoregressive model trained solely on molecules or CLIP models with text descriptions of molecules, BioT5. They actually also works very well. But of course, for those models, you have a different definition for mutation and the crossover, slightly different than larger models where you just use text. And you can see that over those 23 tasks, I think there are some tasks I didn't show in the table, but over the 23 tasks, you actually just with a simple for loop with a very basic evolution algorithm, you can beat the best RL-based algorithm. But you may wonder that if there's a data leakage or so on and so forth. But at this point, my initial goal was to actually show knowledge exists. I didn't even want to show would you leverage this knowledge yet, right? But I just want to show knowledge existed. And this is interesting because even today when I talk to a lot of people about designing molecules and so on and so forth, or designing reactions and so on and so forth, they were telling me that you have to use tools or you have to use agent system, you have to design it very sophisticated way. But in fact, in this line of work, what we want to show is like with a very simple sampling flavor evolution algorithm, you can do it very well. And of course, we not only evaluating on those because we want to understand a little bit if potentially how people are going to use it. We want to see how fast they converge. And this is a example that we compare against the three types of language model that we showed. And you can see that in the first iteration, even if you ask a language model that you want to optimize some property that you're interested in, this binding affinity, that it wouldn't really push it. It does push it with GPT-4, a much better language model, but it's barely pushing it. This means if you only would do question answering, this is what you would get. If you want to find something, you have to find through search, and you ask the answer from a language model. This is what you get. It's just like just started search, and you can see that with the same amount of budget, actually, you can show the convergence. If you cut the budget, because the budget, in reality, this could be experiment budget, right? So if you cut through the same budget, you see that large language models converge much faster. Or, I don't think maybe we don't have the chemist in this audience. Sometimes people ask, what does molecule look like? So I put some examples of the molecules. There's no reason, there's no specific reason to put them, but just if you want to take a look at, if these molecules are really bizarre, but they look okay. And yeah, and then if you care about, you want to design some, they can, that's another nice thing about language model. If you're able to solve those problems, use them to search over hypothesis space. You can use them very flexibly, and they have a huge prior over many things they have been trained on. And I'm going to show you later on, right? So everything is using similar set of language models. You never fine tune them. You only do the search at the inference time. So, and in fact, the only thing you need is an API. And so this is a problem where you have a protein structure and you want to design some small molecule ligand that would bind to this protein structure. And you measure this by some computational scores to see, it's a semi-empirical to see there are some empirical rules about how they interact and how strong the interactions and so on and so forth. And you would see that it actually works very well for those problems as well. But because, we were thinking about those problems might be harder than the previous oracle functions. But still, this is a little bit far from reality as well, but it's better. It's better as a computational evaluation. And you can use them very flexibly. You can optimize your initial pool. This is some scientists may be interested in. You want to start with something you already explored, or you want to maintain some of the, or sometimes when you want to design molecules, you don't want to completely design from scratch because then synthesis becomes an issue. So you want to keep some structures or some scaffold that you have already, the space that you've already explored, and you can see the initial objective values are already okay-ish compared to where you could start from near zero, and now you can keep optimizing those, and you can also perform better than much better than just doing evolutionary algorithm, simple evolutionary algorithm. And also, sometimes you want to do multi-object optimization, and also this can provide us some hint that if there's any difference between an autoregressive based model trained over a reasonably amount of data, quite large amount of data, but not at the level of GPT. And you can see that we have 3 objective composition and 5 objective composition. And here we took 2 strategies. One strategy is just to take weighted sum, just make them scalarize this vector into a single scalar. Or you do some, you take the Pareto frontier, Pareto selection. So because evolutionary algorithm is very flexible, in each iteration, during the selection, you can simply take only the molecular structure, the candidates on the current Pareto frontier. And this provides you a way to explore the Pareto frontier. And this is a hypervolume if you're evaluating the Pareto frontier over the entire space with the maximum to be 1. And you can see in those cases, GPT-4 stands out. Like maybe it has a stronger prior trained. But if you only use an autoregressive based molecular language model, in that case, you can see like with fab objective, it actually becomes much worse or even worse than just regular genetic algorithm. And you could see that is the utopian point. That's the point you are trying to reach. You're trying to push towards, and you can see the volume of the space, that the breadth of the the Pareto frontier explored by language models. And also here, you push it more further, but you don't cover as diverse set of it. Yeah, you can make a lot of observations in those problems, and sometimes it's really stretch out capability of the language model. Sometimes you will see, it's very rare. Sometimes you'll see language model be never to propose any new molecule. That means they are actually bounded by certain maybe by the training set they've trained on. All right, this is my first part.
Yuanqi, can I ask a question?
Absolutely, it's a great time to ask.
Oh, so I was just wondering. So in the GPT-4 based methodology here, how many instances did you find that the models generate invalid molecules?
That's a very good question.
And I guess given the fact that we have a cheap simulation here, that's maybe not a problem. But then, like, imagine if we have a wet lab experiment, then in that case, like, how do you think about this problem of trying to reduce those instances?
That's a very good question. I think this in general touches a very, very hard problem. So I'll give you the straightforward answer first. Back then, even GPT-4, they understand the smells very well. So 95% of the molecules are valid, at least valid in terms of the chemical bonds and stuff, right? The valence. But this is indeed a problem. But I wouldn't necessarily think validity is a problem in general for science problem, because validity are often very easy to be rejected. You just sample more. If something are invalid, you just evolutionary algorithm during the selection, they're just ruled out, right? So just very, very low. You just put a 0 activity. But something worse here is that the quality of the score, the argo function. So some of them, because in science, people kind of like a scientist to look at them and see. For example, the stalking score is something people use very, very often. This semi-empirical based evaluation of the interaction strength. And in reality, it can be, if you ask a medicinal chemist to look at it, sometimes they look at the structure that optimize those scores. Sometimes they don't even capture some key interactions. So this is a much worse behavior than I would say for validity. Validity, people usually able to write some rules to rule them out very easily. But yeah, the natural flaw in designing those argo functions that actually you want it to be related to some experimental, you want to rely on those scores to filter out something to put it into experiment. Those are kind of like more severe problems.
Okay. Yep. Thank you.
Yeah. In fact, that's what we do in this crystal structure generation. Okay, now it's a perfect time to move to the second example. Now we want to level up this a little bit, right? So now, maybe, at that point I was thinking about maybe language models are able to understand the strings very well because there's so many of them and we're going to use them. It's very standard. What if there are some 3D format, like some files that we have? This is a crystal structure, and there are a few challenges about it. First, it's 3D. It stores in floating points, and with a lot of parameters here. And they're highly symmetric. If you break the symmetry a little bit, you have very high errors in terms of energy. You have to evaluate they're valid to see if they don't have a crazy energy. So that's a way that people evaluate materials. And here at back then, Llama was still there. So we just even used the Llama 3.1. And this gives us a very surprising answer in the end. So I just want to give you a very quick overview about this convex flow hypothesis, how people evaluated the if a material would be stable. The idea is that you actually solve a linear programming problem. So you've observed a lot of materials and their energy in natural world and their composition, like A2X and A2X7. And if you want to find A2X5, you would solve a linear programming for the fraction, how much the energy that contributes over this convex hull of the observed materials that share the same composition with you. And you want to find, you are expecting the material that you find for this to below this convex hull, to have a lower energy, more stable than the convex hull that you would guess is for. And, there's just some regular definition. There are two, you don't have to read this, but there are two sets of evaluation. One is on using quantum mechanical calculation, where you want the energy to be strictly smaller than 0, to below the convex hull. Or you have some more relaxed machine learning based evaluation to be below a certain level of the, about, with a tolerance about certain level of the convex hull. Yeah, but still close. And okay, so here's another diagram that we show structure, but essentially it's the same idea. So you have some initial samples, but here you can take something from materials project computational database, and in fact we find having that makes this conversion much faster. To give you some examples, like to make it not 0 shot, like starting from scratch, but few shot. And you make the perturbation to ask Llama 3 to propose new candidates and do the weighting based on the properties. And you notice here, because these crystals are highly structured, and sometimes we do implement a rejection mechanism to check the simple validity. And those are very simple ones that people would check. And but it's not rejecting a ton, maybe rejecting 10 to 20%. It's totally tolerable if you sample enough with your language models. And you do the same. And now I want to show you some very interesting results. And on top of that are state-of-the-art generative models trained over those crystal structures at that time. And what we do is like, if you really think about it, what we do is like we're generating the 3D files and the floating point, a digit by digit, or maybe 2 digits by 2 digits, depending on the language model, underlying language models. And you see if we evaluate it like the structural, because we do this rejection, but there's a stricter structural and compositional validity, and it was not terrible. And if you evaluate the stability, this is by machine learning interatomic potential, and this is another machine learning stricter machine learning interatomic potential. You can see actually get much better than those state-of-the-art general models. And what's most surprising is for this quantum mechanical calculations, if you evaluated it, it's actually like twice better than the best of the state-of-the-art back then. I think it's still better than the state-of-the-art today, but I don't have it here. And the question you would ask is like, how much of this machine learning, because if you're familiar with the crystal structure or 3D structures, they are very sensitive to any of the perturbation or noise or little error that we make on those predictions. And it would ask this natural question is like, do you have to relax the structures using this machine learning based force field first, and then to evaluate on the quantum mechanical level calculation? And in fact, it's yes. But we actually reported how much the energy would change before and after relaxation. And you see 50% of them do not really change, just a tiny little bit. And there are a few, of course, this is kind of like you have this tail here, but only a very small fraction of them actually requires a lot of relaxation. So this shows like language model have been already able to generate very good crystal structures. And they are in 3D, like floating point, 3D coordinates, digit by digit. And also we've shown a few very interesting way of using it because we have some collaborator in this materials project, the largest computational database in the field maintained, and we know that there were some structures in materials project that they don't have very great um, 3D structures yet. And this is the energy above Hall. Like as you can see, we put it straighter as around 0.03, but now it's 0.1. So like very large. And we actually managed to use the Gaussian algorithm over Llama 3.1 to find much better crystal structures than this. It's not a negative value, which would be ideal below the Hall, but it's actually very close, 0.03, within the 0.03 range. And also we did it for multi-objective optimization. If you care about not only thermodynamic stability for this material to exist in real world, that's kind of like a way to say validity. You also care about the hardness of the material, bulk modulus, and you want to push towards this critical frontier of the top left corner, so on and so forth. And there's a few very interesting ablation study that we did because these crystal structures are much harder than the small molecules. As I said, even in the first place, you cannot generate all valid molecules. And also the way that you evaluate them is through this quantum mechanical calculations of the energy. And there are a few settings. The first we compare with actually zero shot, right? So we don't take any iteration, just ask language model to generate structure, and there's no reference structures. And if you look at this, that's actually this. Okay, this color is bad, but this very yellow one, and you can see there's almost no structures that's below the energy EHAL, which means the structures language model being able to generate are almost all no, right? Even compared to this a small computational database, not the full material space that we export. This is a computational database, materials project. And the next thing we do is like, what if I take no reference, but I ask you to iterate. I select better ones, generate over what they propose, and just iterate step by step. It actually works. But diversity complete caps. It actually works pretty well. But one thing you wouldn't see here, the diversity was very, very low across the composition structure. Once you find a good one, it just remain there. What we find is that if you provide the initial pool a good reference, even if you don't have any iterations, language will be able to provide some structures that are novel, but you cannot. So with the same budget, it proposes many repeated structures. You don't see a lot of structures getting proposed. And at last, what we actually use in the end is that you have this iterative evolutionary algorithm to select better ones. Also, you have some reference to push its convergence early, convergence quicker. And then you have the best result. You have good diversity, novel structures. You can propose as many structures as you want, almost. But with a cap at 10,000 that we tried. But this is already a lot. Yeah. For using the reference, but you don't take this iterative loop, just asking language model, okay, here's a good materials, propose a better materials inspired by it. You can propose maybe only, I would say maybe 1/10 of it. All right, any question about the second part? Cool. All right, I'll move to the third part. The third part, I want to challenge language model with an even more challenging problem. Is a sequential decision-making problem. Actually, this problem is very similar to a mathematical reasoning problem, but it's just in the chemical context. So the problem is following. So you have some molecules, and you want to try to solve the inverse problem to see how do you synthesize the molecules. And how do you synthesize molecule have a space of actions, those red curves. And you want to but you do it reversely. You want to decompose these molecules by a list of actions, and after you apply these actions, you get some outcome. And this is a direct acyclic graph. And the outcome, you have a space of predefined set of those outcomes that you can buy in reality, you can purchase. And you want so to define a successful path, you would like the leaf nodes in the stack would house it in a purchasable database, right? So this is pretty much similar to a mathematical reasoning. You want every step to be valid, and you want to reach your final answer. And those intermediate actions are just reactions to break down this molecule, and they have the intermediate one that you don't see them in the purchasable set yet. You have to continue to decompose them until they are all in a predefined set. And how do we write this? How do we represent this in text, right? So that's already a challenging question on its own. We tried two of them. First, we tried to, because this is a DAG that you could represent those highly structured data points in terms of JSON files, and you can put a nested JSON to denote the nested structures, or you can flat them. You make it more like a linear structure, but they have some dependency across those linearized storage. Yeah. In fact, in reality, we find the second works better because possibly there was a lot of JSON files trained over language models. And how people solve this classically, because it's a very nice search problem. And you can use Monte Carlo tree search or A-star search, the variant of A-star search. And you can do a better heuristic by using a machine learning, the neural networks, to train a heuristic to predict what action to pick. And you combine it with a search algorithm. And when we start thought about this problem, initially we can thought about this like replacing the neural network predictor heuristics with large language models, or the other strategies. Don't use heuristic at all. Don't even do the search as what you would do with classical search algorithm, but just generating this whole thing, sampling this whole path together. And in fact, what we see is like when we try to replace the neural network-based heuristic with large language model here, with this Monte Carlo tree search, retrostar is a variant A-star search. And here we use GPT-4o. Is that you can see for those easy paths, you can still do them okay-ish. But this easier like in three decision steps, very, very short. But for those harder paths with more than 5, 6 steps, they completely doesn't work. And what it works is actually we turn the mind completely to sample this entire path. So the intuition is following. When we started working on molecule optimization, there were a lot of people trying to let language model to mimic what human scientists would do, to start with a molecule and keep adding to the molecules to optimize it until you find a better molecule. But the point is that this is not sampling, right? You really treat language model as human. What we really want to do is like treating language model as a probabilistic model, not a human. And in the probabilistic model, you would sample more, and you would only keep the promising one to further explore. You would not spend much more time in those bad ones because it's just a bad probability that to sample them. And that's what we do. And after we figure that out, that okay, we should not ask language model to revise a bad route step by step, but instead we should focus the budget on generating more routes and only keep the promising one and explore the promising one more and more, instead of just editing over and over again on the bad ones. And that's what we do. And we do the same thing. We could have some initial samples, but this initial samples is defined by a different type of similarity towards your target molecule. You may have a reaction database of molecules that you can synthesize, but to a different target, but you can measure the similarity over the target molecules. And you ask language model to make perturbations over the path, and then you weighted them, and then you resample, and you do the same loop as the evolution algorithm. Only slight changes at how you define the score function, how you define evaluation a little bit, how you define the format, but everything else is just simple evolution algorithm. And in fact, with this fix, we actually can get much better result. And in some scenarios, we use GPT-4o and the DeepSeek R1, and actually get very good result. It's on par with the CCR searching algorithm under the same budget. And even if you look at it, that if you give it a lot of budget, like 500 cost of those search algorithm, and also for language models, you can actually beat those state-of-the-art searching-based algorithms. And later on, there was a follow-up work that actually they improved upon us very recently. They replaced evolution. They would argue evolution algorithm is not the best search algorithm, which I agree. And they replaced it with a tree-based Monte Carlo tree search. But also they still sample reaction pathways, and they would use Monte Carlo tree search to define what path to focus on next, and to come like a sampling over based on the example of that path and keep exploring. In that way, they actually further improve our performance, actually much better than maybe what we'd be able to do. And there are a few interesting observations because this is a rather challenging task. I didn't even think language models would be able to solve it at the first place. And but this does reveal a few, very good points about language models and what it would fail. first, the tree structure is hard because it's so nested. Complexity is really challenging. This is an ablation study over an easy data set and slightly harder data set. And you can see, whenever I'm talking about how much it helps here, it's not like a 1 or 2%, but it's like a 30, you can solve 30, 20, 10 more puzzles than you would otherwise cannot solve. And you can see that it drops significantly if you use the tree-based structures. And also we have this kind of like a initial pool, and we use some retrieval to help to augment this space. And what's interesting is that initially we want to see, if we put some example roots and help, we want to see if this correlates with how similar the roots could possibly be to the target molecule you're interested in, right? So if you think about the mathematical problem, is that you're solving a problem and you want to measure if a similar problem would help, if that's the similarity between the problems helps, or the template of how to solve the problem helps. And in fact, what this reveals surprised us is that actually if you put a random roots, it helps a lot already. But of course, if you put a similar puzzle, that helps even more, but not as significant as the format. So what it shows is like the format helps the most. And then having some similarity between the root, between the puzzles, that also helps further. And the other thing would be, and this is one thing that are maybe slightly different from mathematical reasoning, is like in mathematical reasoning, maybe the only thing you have is maybe 0 or 1, very sparse reward. Here we put a very crucial partial reward, is that we put some partial reward by evaluating some part of this DAX to evaluate how good they are based on very, very poor heuristics. And you can see even with very poor heuristics, it improves like 50% on the solve rate. Because otherwise it would be just keep either accept or reject. And you only accept something when it's good enough, when it's already a good path. And with this 0, 1, if you think about from rejection sampling, that makes a lot of sense. And it's very hard to find a good one. And if you find a good one, you only keep the good one, and that's very inefficient, right? But here we put some continuous value over the reward. I believe people also do this in some of the math or coding problem. And prompt engineering helps, but it doesn't help a lot, right? So we've tried to change different types of prompts. And prompts, it's great. It's a great thing that prompts always helps, but it helps the minimal compared to everything else that you would do with search and sampling. And also one more thing you can do is like you combine this. You not only want to design molecule, but you also want to design at the same time their synthesis path, this direct acyclic graph. And that's what we do. And you can do this. What I showed you before was the inverse problem. You take the target you want to do, you reverse engineer, where you should start. But now you can do is like you start with whatever you want, and you see how you construct the target. And you want to optimizing the target towards some desired properties. And you can iteratively optimize these things as a whole. These are for chemists if you really want to use it. Okay, this figure is a little bit hard to read, but essentially the point here is that once you add this design compared to what we did before with just optimizing the properties that you care about, but now you not only care about the property, you also care about if you can synthesize this molecule. Because even if a molecule demonstrates great property, if you cannot synthesize it, you cannot make it in reality, it's useless. And it doesn't really hurt the performance much, but it guarantees accessibility. And this is again example for some chemist. If there's chemists in the audience, if you want to take a look at it with some of the reactions, right? Okay. I think now I want to kind of like go into the takeaways and wrap up. But if there's any question about this part, it's a great time to ask. All right, we can do that in the end as well. While we were doing this, our collaborators also applied this to some more, I would say, less common structures in reality. That this transition metal complex design, and also showed very amazing behavior there. We also applied this. It's a very very minimal paper to design protein sequence for protein engineering. It also demonstrate quite reasonable results there. Because along the way, my goal was to challenge language model. What couldn't I get from language models about science? Like if they are well defined, if they are well defined search problems, in terms of complexity of the structures, whether it's in 3D, whether it's very long sequence, or whether it's a sequential decision making, it has very very challenging kind of like formatting, so on and so forth. And in the end, among the problems that I have broad interest over many stats problems. Among the problems that I've tested, they actually all solve them very well. At least, I mean, I'm not talking about if there's data leakage and so on and so forth, but it's because even if there's data leakage, you cannot query by zero shot. You cannot query by just Q&A, right? So I'm just showing those actually exist, but you have to do it properly through search or sampling to respect the nature of language models. All right. And there are a few things that I'm thinking about, and there are some future works that I'm currently doing. Is that I want to start with some summaries. Like I always reflect why language model works this way, and I really appreciate that along the way that I challenge language models with those hard problems, I do see some of their limitations, and that makes me feel like they are not just that we are creating a human that may be stronger than us, but more like they do have the boundary. They're trained over the data, and sometimes they would fail if you challenge it more enough and systematic way. So yeah, so I think this first I want to state the takeaway is process very strong, and if you don't believe this is science, but there are also other people testing this in physics, in symbolic regression, or biology. We've done a few things, but at least chemistry that I mostly focus on, and you can do pure inference time sampling. Fine tune, and also we've done some experiment of further fine tune the model at some of the problems, and they actually further help, but it's not the most significant part. Well, some people would think you would only be able to solve them with fine tuning. That's the point I would try to make. And how, and I went back to think about, how language model work. They are probabilistic models. So, I really want to kind of encourage more people to think about this through sampling perspective, because there's very long literature, like a lot of things that people are thinking about. How do we control the distribution that we want to sample from? How do we do it efficiently? How do we solve the issue of diversity of the mode collapse and so on and so forth? Those are the questions I'm very much interested in. And how do we make them converge faster and so on and so forth? And and then why language model would work? It was all of the result, every result, the three main result that I showed you here. Initially, when I saw them, I was shocked, and I keep asking myself like why it worked, because I was trying to my hypothesis while I was doing that was that they could somehow work, but probably at some point for this more complex problem, they would fail, right? And I would say, and now, based on some of the observation we have, there are huge knowledge base. Even though, we compare with some not large language model, but like molecule language models. If you think about it, they've never trained on the data of the internet, but somehow larger models solve this catastrophic forgetting issue, even though they train on the internet data. But you're still be able to trigger the part of the knowledge that you want. This is amazing. And why not? If they don't forget about the molecules they've trained on, and they're only adding more, capability on top of it, then it's a foundation model at the same time for molecules, not only language-based models, right? And also they have learned from math and code, and also they have very general conversational capability, even though it's debatable if this is interpretability, but this is already much better than just looking at the output of black box, models, right? You can chat with it, and the chatting capability provides flexibility on using them very flexibly. That I have a few cases that I've showed, like multi-objective, optimizing initial pools, finding structures in different ways, so forth. And the question I'm thinking about is like, where is the limit of larger models, right? I really want to see what's the boundary. I'm really happy when I see language model cannot propose any candidates, any hypothesis. Then I'm happy that the language model are not just something that mysterious, like compared to before. And for scientists, it's really have this, in the old days, what we do is like we build probabilistic models, and we first define a best distribution. We will say, okay, these are the distribution we are interested in, this type of things, and then we build a data set for it, and then we train a small probabilistic model on it, generative model, diffusion model, or whatever, and then we draw samples, right? But now we really shift the work from defining this best distribution towards we already have a huge good coverage of very general language model. We only need to design the evaluation better and better, and we use that to lead the search. And maybe we can connect this to the lab. I know a lot of people are connecting this to a lab experiment, high throughput, to iterate search in this type of space. And another thing that's kind of mysterious to me is like, I guess is in general, like all the architecture people use for different problems these days converge to transformers, and also about tokenization, right? How come if I tokenize a floating point that you are also able to get it very precise way? And also the interpretability, I guess this is kind of like there's a community on mechanics interpretability. I used to work on those things maybe 3-4 years ago. And I'm very interested in how do we visualize the mind? How do we visualize the search route or the landscape of language models? And what are they based on? Maybe similarity. Yeah, this is my last slide, I promise. So, what are the reasoning capabilities, right? So, are they actually, based on semantic reach or similarity embeddings and then do search over that? It would be very interesting to see how they actually do this. How do you actually, when you change your prompt, you activate different space of that and you do some local search over that space or so on and so forth. And I haven't talked about anything related to tool use, and that's something I'm thinking about these days. Is that everything I'm talking about is orthogonal to any tools or anything. It's a very well formulated problem, and you only need the API call, and you only need a for loop to define this evolution algorithm. Yeah, and also, what are the fundamental capabilities should we then achieve with fine tuning? If fine tuning is not, if we don't have to fine tune it for a specific task to solve that task, right? So we probably want to we're thinking about fine tuning a little bit. What are the fundamental capabilities we want to gain instead of just make it a specialized model? Just train on this for proposed better molecules instead of maybe something that human would align with human better, instead of wasting the budget, not wasting, but putting the budget into fine-tuning them to a specialized model. And the last point is really maybe the takeaway I want to emphasize. So today, what I've been talking about so far, even though I'm talking about in the context of natural science, chemistry, biology a little bit, but the problem formulation I started with is really was informal science, computer science, mathematics. So the key difference is like in formal science, for example, in computer science, we really have a cheaper verifier than is much cheaper than solving the problem. So you can form it in this way, right? You have a good verifier and you just keep iterative searching loop to see if you have solved the problem. But in natural science, it's actually so different because you don't even know, you have a rough goal, but the way that to achieve the rough to the goal, the objective, the score function, the oracles can be very uncertain. You may change them, you may at some point after you've seen some results. So you really don't know what to explore before you see the results. So that's the real difficult part for this to automate the science. And that's also the most appealing part for this problem. And that, in my humble opinion, I think no previous computational paradigm has been able to achieve the automation. Yeah. All right. So with that, I'll wrap up my talk. Yeah. Thanks a lot for your attention, and happy to discuss. And everything is open source, by the way. If you want to play with anything.
All right, that was great, and I think we've made great time. Let's give our speaker a round of applause.
Thanks. Yeah.
Right. I don't know, Jake. Did you want to check in the room about questions?
Sure. Oh. Okay, let's start from here.
Yeah. Yeah. Hey. Yeah. Charles is
fun talk. So would like you to kind of expound a little bit more on this scientific knowledge emerges in LLMs in two different ways. The first is scientific knowledge is kind of a subset of knowledge in general. And so how much of what you're saying is basically that, yes, knowledge emerges in LLMs. And the second part is typically when we think about scientific knowledge, we're looking for like a synthesis of information, so that you kind of take a whole bunch of things and you're trying to come up with, say, a simple theory or a complex theory, but something that allows you to then from there generalize. So would you say that this has been produced here?
Okay, that's a very good question. Yeah. I think my initial motivation was thinking about, large language model has been mostly training on general text, and there was always been, I started with a very well-defined problem, like people wanted to understand if language model has been trained enough on science, and if the scientists can use them to solve their own problems. That's where I started. So I would say, yeah, it's a subset of general knowledge, but the first thing you want to test is like if they actually understand the format, for example, if they understand the structure of it, and usually they are highly structured, they are in complex forms, and yeah, I would say this kind of like sense of reasoning would generalize towards this based on the structure. I think, okay, I would summarize the following. So my initial motivations was to answer the question very specific about if I can use this to help scientists. But later on, when I dive into this, I see a lot of more complex structure, for example, generating floating points, generating this JSON file, nested JSON decision-making steps. I would say this would make it generalized. I would say the same thing would happen for a math problem that share the same structure, right? I would say, yeah. Does it make sense?
Yeah, it does. Thank you.
Yeah, thanks. That's all. Yeah.
Can you hear?
Yeah.
So I have a question about, you mentioned we should treat the language model as a sampler. I agree with that. So how are we gonna do it in the multi-agent scenario? Because in the multi-agent scenario, we kind of like treat it as a human, not as a sampler. So how would you like combine the idea of tree language model as a sampler in a multi-agent framework?
Very, very good question. That's certainly a problem I've been thinking about these days. And I think there are two ways. One brute force way I would say is like we can separate the well-defined part, the optimization loop, the search problem, from the problem where you require automation. That's one way. Just distinguish them, right? So treat the sampler only that part as sampler and the other part as human that controls this process, retrieval information, make decision about what to explore next, so on and so forth. But keeping this search part well formulated. That's one way. I would say the other way would be for multi-agent. Well, okay. So I feel like there could be a few ways. So it could and some of them are pretty specific. For example, if you can think about the roles of different type of agent and what things they do. I think when you talk about multi-agent and for agent, that has to be humanized in some sense. The key difference lies at which part you want them to humanize. I would treat the retrieval to decide what to look up literature, to use tools, those kind of capabilities as humanized, and treating in general, what roles different agent takes and how they evolves those part as sampling. I think the short answer is like to distinguish what part we wanted them to be humanized, right? I think there are certain parts if we have to make them humanized to function, and there are parts that if we can make them well defined, then we can leverage it in sampling.
I see. Thank you so much.
Any more questions?
I think there's
Actually,
a question on Zoom. Yep.
Hi.
Trang, go ahead.
Yes,
Yeah.
I have a question. Can you talk a bit about the runtime of the LLM planning, especially in relation to the classical approach?
Oh yeah, the bottleneck is language model calls. Yeah, I think you're right. Yeah. So for example, when I was doing this sequential decision-making problem, the bottleneck was language model calls, especially we using GPT-4o, and the call wasn't so fast around that time. And the classical searching algorithm, they use a machine learning based model as heuristics, and that's usually very quite fast. But actually, we did benchmark this a little bit in our. So you have we had two ways to benchmark this. First is based on number of calls, right? So just assuming language model calls are going to become cheap in the future, just evaluating number of the calls. And at that, you can see that for 500 calls, we get even better result than classical search algorithm sometimes. And but if you think about the running time, I think we are maybe twice slower, roughly. We have some ablation, to benchmark the time in the paper.
Yeah, and I remember you mentioned you also use DeepSeek, right? Is it?
Yes,
so
it's much fun. It helps. Okay, yeah, we also use DeepSeek, and DeepSeek is much faster and cheaper. more helpful is cheaper. And but one thing I want to highlight here is actually I forgot to mention another thing we observe is that we also check the DeepSeek R1 and S1, like with reasoning and without reasoning. And one interesting we figure out here is that the performance doesn't differ much. Like if you already have the search algorithm, it doesn't help much if you have a reasoning model. You have a lot of reasoning traits during the language model prompting versus without it. That's another interesting behavior here. Yeah, but yes, so depends on which DeepSeek. When we use the non-reasoning version of the DeepSeek, I think it would be on par with the search with neural network based heuristics. Yes.
Yeah, and also looks like the performance report here is basically the same as using GPT, right?
Yeah, but I believe this row we report is for R1, the reasoning version, but we also have a ablation study, which are pretty similar in performance without the reasoning mode. Yeah, and that's much faster.
Okay, great. Thank you.
Yeah, thanks.
Yeah, I know we're at time, but I want to just maybe get one quick question and just hear your thoughts about it. So I was just wondering what you think about the exploration limits of these non-parametric approaches to scientific discovery with generative models. Do you think there is a fundamental limit there? Is there any value in trying to model this in a latent space? And like, yeah, what are your thoughts about that?
100%. It's a fundamental limit. The limit comes from two parts. One part is even more fundamental, is that the corpus that language model has trained on. You do observe this. Like right now, we are pushing something, collaborating some experimental folks at the Broad Institute. We are trying to push some antibiotics into the lab. And what you see is like, there are two types of exploration limit. Maybe I'll start with the simple one. The simple one is like the evolutionary algorithm, even though you put some diversity-based cluster and so on and so forth, they would converge to similar structures, what we call scaffold. It's like the large unit of the molecular structures that supports the full structure. And you have some center scaffold with fragment on the side. And the scaffold similarity has been very low. And that shows you the diversity, but this can be solved through sampling. Like in sampling problem, like you face this mode collapse and you can solve it. You have various ways to solve it. But this point us even more fundamental. And the simple thing at the interest of time that we did to push for experiment was to ensemble. Ensemble always helps, it's just costly. And what you see is that after round of more computational intensive or ask the chemist to do filter, what's left over still somehow share a similar scaffold sometimes. So that's the fundamental limit that the language model has been trained on. That's something we otherwise wouldn't know if we don't do this. Yeah, that's always something I'm trying to do. Right now, I'm trying to really push those to talk to scientists if we can make new discovery with those things. And that was the negative part, but I would want to share some early results on the positive part. It's very impressive that you don't need much of the training, and you can already automate a lot of this process. And I think it's very likely to lead to some new discoveries. But we haven't tested it yet, but at least a human scientist was impressed. But yeah.
That's pretty cool. Okay, like yeah, I think definitely we'll follow up more about this later. Okay, so I guess let's thank our speaker again. Yuanqi, we have some one-on-ones that are scheduled for later on today, so I will have the scheduled up for that. Okay, thanks for being here.
Everyone. All right, goodbye.
Bye everyone.